All right. Okay, so welcome everyone. So today is the last talk for the academic year, and it's my pleasure to welcome Saurabh Malani, who will be talking about nonlinear identification with partial information. Thank you, Saurabh.
All right, so yes, thank you for the introduction and thank you for the chance to speak at the seminar series. So yes, today I'll be presenting my recent paper, which is on nonlinear identification with partial information. It's accepted and waiting publication, but if you want to read it, it's also on archive. But to begin with, I thought I'll start with a brief introduction about who I am. So my name is Saurabh Malani. I am a PhD candidate in chemical and biological engineering at Princeton University, and I am co-advised by Jose Avalos, who's at Princeton, and Yanis Kavrikodis, who's at Johns Hopkins. And my research interest is in physics-informed machine learning applied to biotechnological applications. So here, like I've got two advisors, so I have my 2 feet in two very different worlds. Through Jose, who's an experimentalist, a biologist, I've gotten personal experience with running my own experiments, especially when it comes to bioprocesses. So I've got an idea as to what kinds of data these kinds of biological processes can generate and what kinds of data I should be expecting to generate. Through Jan, through the machine learning world, I've learned how we can use data to learn and understand physical and biological systems. And through I've learned like what kind of data we expect to give us inputs to our machine learning models, like what kinds of data does it operate best on. And I've experienced this often this a little bit of a disparity as to what kinds of data the machine learning scientists would like or expect to train their models and what data they actually end up getting from the experimentalists. And this disparity was one of the motivations behind in this work. So more formally, what this work is about is a nonlinear system identification approach to develop a surrogate model for dynamical system that we care about studying. So in this work, we'll be focusing mostly on time series data, and we're going to assume that the underlying dynamic system is more or less deterministic, such that we can express the underlying dynamical system as a system of ordinary differential equations. Where now here, the goal of system identification is to learn the right-hand side of the ODE is here the time evolution operator F. Once the surrogate model is developed, it has many applications, which makes this approach useful, which is that with a surrogate model, we can do quite a bit of optimization, which could be, for example, to maximize the productivity of a certain process, or to maximize the efficiency by minimizing production of certain byproducts. With a good optimization, we can even go further and implement this optimization in real time through control schemes, for example, through model predictive control. And also, when it comes to understanding the system, um, with a good surrogate model, we may be able to extrapolate what the system behavior will be beyond the parameter and state space that the model was trained on. And in doing so, we may be able to guide future improvements in the experimental systems. And in some cases, we can even predict failure modes in cases where we don't want to necessarily push the experimental system all the way till failure. So here, once again, coming from both worlds of experimentalists and machine learning scientists, I was looking at what kinds of information we often have to draw from in order to train our machine learning models. So here, broadly, we have two classes, which is our actual experimental data, stuff we get from our experiments, and we also have quite a bit of previous knowledge, whether it's from like a priori models, physics models, or mechanistic models that give an idea as to what the underlying system is doing. When it comes to experimental data, like I mentioned before, there's often a bit of disparity as to the kind of data is actually generated and what the kinds that we want for our machine learning models. So the first thing I'll talk about is how can we train from such messy data? If you ask any biologist or any experimentalist really, when you are they often care a lot about what their data is and because it relates directly to their system. And often machine learning people will have to do some sort of data cleanup or pre-processing that involves modifying the data. And this often may affect how the result of the trained model will be. So the first part of my talk will be talking about how can we train from such messy real data we get directly from experiments with minimal pre-processing or modification needed. The second part involves combining data-driven models with physics models. Now, data-driven models have become very popular in recent times because computing power has improved significantly, and we've also gotten better and better abilities of generating big data. However, that doesn't mean that a lot of the physics mechanistic models developed in the past few decades to centuries are no longer as important. In fact, they often give a very good physical impression as to what the underlying system is doing. The second part of my talk will talk about how can we also incorporate existing physical knowledge into our data-driven models, combining black box data-driven with white box physical models into this hybrid gray box physics-informed machine learning models. So first now I'll talk about the first part is on training on real data and what do I mean by quote unquote messy real data. For machine learning scientists, ideally the kind of trained data they would like would be trained data that is well organized. For example, in the case of time series data, it could mean that data that is well organized in the temporal grid, that it's sampled at very regular time intervals. Also, they may want full observations where at each sampling time, you can measure the entire state of a system, all the important variables needed to describe the dynamical system. In reality, however, we may face some data pathologies. For example, in real data, we may face the issue of partial observations. In the context of biology, for example, we have many different analytical techniques to describe what's going on in the system or to probe what's going on in the system. There can be, for example, HPLC, GCMS, flow cytometry, or different sensors such as pH, dissolved oxygen, or turbidity. Each of these analytical techniques measures a different part of the system, but often you won't use every analytical technique at each single data point, and you won't even use each analytical technique at every single data point throughout time. What is resulted is in this case of partial observations, where at each sampling time, you only measure a subset of the full state of a system. Another data pathology that we may encounter is that of variable time sampling, which means, and this often happens because in biology, you may find that a lot of sampling actually happens manually, and it's unreasonable or tedious to enforce that it always happens at the exact same time intervals. And so some sensors just may not operate at regular time intervals. And so you may have this characteristic where the training data you get may not be sampled at very regular delta t's. And often you would experience both of these pathologies simultaneously. And this is kind of what I mean by messy data, and I'll talk about like how people currently work with this data. So many of the current methods involve some sort of pre-processing on the training data to make them more conducive for machine learning. For example, for partial observations, if the number of anomalous data points where you have some data missing are few, the simplest approach sometimes is to just delete that data point entirely. But this is obviously not feasible if this is a more broader characteristic of the data set. In which case, the approach many people do is some sort of imputation, which is a way to intelligently replace the missing data to essentially complete back the data set before you do statistical analysis of machine learning or trained machine learning models. This kind of imputation can be as simple as a mean imputation approach, or for time series, you may use a last observation carried forward approach. It can get more and more sophisticated with machine learning techniques such as k-nearest neighbors or neural networks such as autoencoders or GANs. A lot of the imputation techniques, however, if they replace the data in a way that doesn't necessarily reflect what is the true underlying dynamic system, this kind of imputation may actually introduce biases to the data set that may affect what kinds of models that you train afterwards. For variable time sampling, again, one of the simple solutions is a kind of deletion of the anomalous ones. That's not reasonable. You may try and find if there is a base delta t that you can a common denominator that you can fit all of the data samples to. That's not possible. Often there will be some sort of smoothing algorithm run or some sort of interpolation that basically reconstructs from this data a data set where it is actually very well arranged in temporal time. Again, all of these include biases to the data set by enforcing some sort of smoothness approximation that may not be reflective of the underlying system. Some approaches that actually involve actually taking into account the fact that the samples are arbitrarily or variably sampled would have maybe, for example, including the timestamp as an input directly to the model. Or for example, my approach that I'll talk about very soon is to use a method that very naturally accounts for the fact that there may be varying delta t's. So here again, the main task that I had in hand was to kind of develop a methodology that can train on data with such pathologies without any pre-processing that requires data modification. Before I go into the methodology, I'll first introduce the toy example from which I will demonstrate this methodology on. And as a chemical engineer by training, I chose a chemical reactor system. So this is a simple chemical reaction. It is an A going to B reaction. It's exothermic, so it releases energy. It's a continuous flow, so there's a constant replenishment of substrate A, and the unreacted substrate and products are also washed out at the same flow rate. And there's also a heat transfer between the reactor with a cooling jacket. So this system can be described by two ODEs, one for a dimensionless concentration or equivalently conversion, or and a dimensionless temperature. And this system is parameterized by three parameters, which is the Darm-Kohler number, the B, which is a measure of the energetics of the reaction, and beta, which is a measure of the heat transfer of the system with the cooling jacket. Here we assume that B and beta are kept constant as properties of the experiment, and we only have the ability to change the Darm-Kohler number. With that, we can generate bifurcation diagrams with respect to the Darm-Kohler number. Sorry. Bifurcation diagrams where we find hot bifurcation points at 0.28 and 0.42 values of dA. Below 0.28 and above 0.42, the system goes to steady state at the values shown by the curves here. And between 0.28 and 0.42, the steady state is unstable and the system stabilizes to a stable limit cycle with the maximum and minimum values given by these two curves here. So with this toy example in mind, the first part of the methodology is in formulating the neural network training as the learning of the right-hand side of a system of ODEs. The alternative to this is the more straightforward approach is to train a discrete time predictor, where given x at the current time t as an input to the neural network, we get the predicted value of the state at the next time step directly from the neural network. However, a more intuitive way for dynamical systems is often to instead train a differential predictor, where given the state x at the current time, the neural network will instead predict the time evolution at the current time. And for our system, because it's time series data and it's deterministic, this is best expressed as an OD system, where now the neural network here is learning the right-hand side of the underlying ODE of dxdt. This, as it turns out, is very important in allowing the neural network to train on data that is sampled at variable time sampling, and it also allows for more easy implementation or integration with existing physics, and I'll go into that in a couple of slides. But first, I want to talk about how can you get the neural network to learn dxdt when you only have observables for the state x. And to do so, we can leverage the very well-established field of numerical analysis and numerical methods, specifically when it comes to numerical integration. For example, we can look at the ResNet, which is now a very classical neural network architecture, as an analog of the forward Euler integration. The ResNet is characterized by skipped connections, such that rather than the neural network predicting the output directly, it instead just learns the difference between the input and the output. And this can be seen as an analog of the forward Euler step with the delta t parameter just hard-coded into the neural net. And so in this way, if you take out delta t again, and as delta t goes smaller and smaller, this neural network should converge to the derivative dxdt. The forward Euler is a very simple numerical integrator scheme, and it's only first order accurate. But once again, we can use numerical methods to find better numerical integrator schemes to template the neural network on. For example, a fourth order Runge-Kutta integrator, which is fourth order accurate, and it takes 4 passes through the neural network to generate the predictions at the next time step. This kind of approach has been around for a while. Like this diagram, for example, was from a paper from back in 1992. But this kind of approaches have come back into favor, like from the paper of neural ODEs. And through those kinds of advances, we're not even restricted necessarily to using this kind of very straightforward explicit integrator in our framework. We can really use any numerical integrator. But we have found that practically this approach here, which is more of the discretized and optimized approach, which offers a good balance between accuracy of training as well as ease of implementation and computational speed. these steps can be very easily coded into a machine learning package such as PyTorch, and gradients can be calculated simply by automatic differentiation through each of these steps, and it is also allows for faster computation in that sense. So with this, I will first show how templating the neural network on this kind of a numerical integrated framework allows you to learn the right-hand side of an ODE. And demonstrating this on the Upal-Repur CSTI example again, we can see on the bottom right-hand figure that we're able to learn the right-hand side. Here on the x-axis, we have the output of the true right-hand side, which is the output from the ground truth equations here. And the y-axis are the output from the neural network model. And as you can see, all the points lie on the identity diagonal, showing that we're able to learn the right-hand side. The right-hand side can be seen as a measure of the short-term predictive power of the network because it shows how the system will be evolving at the current time point. Similarly, the bifurcation diagram can be seen as a measure of the long-term predictive power of the network because it measures how the network will behave at steady state. And if the network doesn't have a stable steady state, then what stable limit cycle does it converge to? And we can see here as well that in long time as well, we are able to observe very good reproduction of the bifurcation diagram. Next, now that we've shown that templating the neural network on Arc4 allows you to learn the right-hand side function, the next step is that this same framework also allows for training on data that has variable time sampling. If we had the old discrete time predictor network, we would be hard-coded to a specific delta t of steps, and if the data doesn't lie neatly at delta t intervals, it is difficult to take into account during training. However, in numerical integration, delta t is a very natural input to integration, which can be leveraged to generate predictions at any time point that we desire. So from a discrete predictor, now it's a continuous predictor, and we can integrate to whatever time point data is available. So now we can train on data no matter where it's sampled. Over here, I will also introduce a few practical considerations because in my paper, I am using an explicit fixed time step Runge-Kutta integrator, which is that when you use this kind of integrators, you'd also need to control the max delta t of the solver as a hyperparameter. For example, if the data that you have is spaced in this kind of manner, and you have the RK4 integrator take only one step between each successive data point, you may find that the time step may be way too large for the RK4 solver to be accurate. Conversely, if you impose a max delta t value such that if the data points are too far away, it will just end up taking multiple steps in between successive data points. In doing so, the RK4 solver will be very accurate, but because you're taking so many steps, you're going to vastly increase the computational power needed to train this network. So if you find a good balance between these two, where you set a max delta t that is small enough for the RK4 solver to be stable, but large enough for computational tractability, you'll get this best balance between the two things. The next pathology that I'll introduce is how do we train on data that has partial observations. Here I'll introduce two terms, which is autoregressive training and teacher forcing training. In autoregressive training, the model is only given an input at the first time step. So this time series, so it's basically an initial value problem. So you give the initial value at time 0, and then henceforth, the model feeds back its predictions back to itself as inputs to generate an entire prediction trajectory. Then you can take loss wherever there is actual data, and then you train the network from there. In teacher forcing, you start the same way from T0, but the moment you encounter a point where there is a real data available, you stop the integration there and you restart it by taking in the real data point as input now. So in this way, the trajectories in teacher forcing are much shorter, and this approach was first introduced in the context of recurrent neural networks, which took in very long time series, and it was shown that teacher forcing approaches actually help training of the RNNs better, especially early on in the training regime where the model was far from convergent. And I also see similar behavior when using neural networks, that teacher forcing really speeds up training early on in the training regime. So when we extend this to the multivariate case, and specifically the partial observation case, If we were to stick to a fully autoregressive training regime, here now we have two variables, x and y. Once again, the autoregressive case would behave similarly, that we only give it input at the very first time point, then generate an entire prediction trajectory from there. However, for partial observations, there is an added complication that even the initial condition can also be partially observed. And if you don't have an initial condition, you can't initialize the network to generate the prediction. Here we get around this by introducing an additional training parameter for the neural network, where the initial condition is also trainable. This was also inspired by RNN literature, where shown that that in RNN they have hidden state and that often needs to be initialized. Some people may just initialize it to zeros, and as the dump trajectory, it will converge down to the right manifold. Other people have shown that if you have the hidden state at time zero also be trainable parameter, it helps the RNN to learn the right dynamics better. And so we have the same approach here, where if the initial condition is not available, we just give it as an additional training parameter that the model can learn during training. The issue with this now is that, especially early on in training, when the initial condition is far from the true value that it should have been, that this drastically throws off the trajectory that is predicted, especially for the autoregressive case, because in autoregressive predictions, errors tend to accumulate over time. So here we extend the idea of the teacher forcing now to the concept of partial data. Here sort of the same way, where at time zero, the model is initialized with the real data point if available, and if not, with a trainable initial condition, and we integrate it till the next time point the data is available. Here we pause the integration, and for the next input, we use the real data for features that have real data available, for example, here y, and here x does not have real data available, so we will keep continuing on with the prediction from the previous iteration. And in this way, we can see that the effect of a bad initial condition gets washed out down the trajectory, preventing the training from getting derailed just because the model was far from convergent. So this is the approach that we use for training on partial observations. And I'll show how this shows in some results on the URP CSDR model. So in the URP CSDR model, we first start with a base case situation, which is case A. This is the same graph that I've shown you a couple slides ago. In case A, we have basically what I call the ideal data, where the data is very finely sampled in a way that the RK4 integrator only needs to take one time step between successive data points and still be accurate. The data sampled at fixed delta t's, it has full observations and initial conditions are given. So this is the ideal scenario in the base case. In case B and C, we reduce the frequency of sampling of the data down to 0.5. 0.5 is too large for the RK4 integrator to take in a single step. And we can see that if we still insist or force the RK4 to do this in a single step, we kind of lose the good reproduction of the bifurcation diagrams. Here, this in blue here is the predicted, and in black is the true ground, is the ground truth. But for the same data, if we now restrict the largest time step that the RK4 integrator can take back to 0.1, we get back the very good bifurcation diagram predictions. In cases D, F, and URP-BB, we introduce incrementally the complexity in training data. In case D, the training data is now sampled at variable data delta t's. In case F, the data also has partial observations. And finally, in the URP-BB case, the initial condition as well is also partially observed, so it needs extra trainable parameters for the initial condition. And despite increasing the complexity of training data, we can see that this approach is very robust, as can be seen from the very good reproduction still of the bifurcation diagrams. So far I've talked about how this methodology can be used for training on quote-unquote real data or messy data. And the next part is how can we incorporate existing physical knowledge into our data-driven models? And the rationale for doing so is that while data-driven techniques are powerful, mechanistic and physical understanding of processes is as well important. And combining the two can allow for more physically interpretable models that have greater generalizability and extrapolation properties. And this can also allow for better training and better convergence on fewer training data points. And here, again, our previous approach of framing this system identification approach as a learning of the right-hand side of an ODE comes in useful because a lot of previous physical knowledge does come in the form of dynamic rates. For example, in chemical engineering, we would be faced with knowledge about reaction rates, diffusion rates, or microbial growth rates. All of these are best expressed in the form of a time derivative. And if a neural network is also learning a time derivative, it becomes more straightforward as to how can you integrate these two into a hybrid model, which I will explain with some examples soon. A lot of this gray box kind of architecture in literature is done in the form of correction models, where the black box model is tasked with just learning the correction from the white box physical model, which may be approximate or may have stuff missing in its formulation to get back whatever's missing for it to fit the data. The idea behind the corrective models is to reduce the onus on the black box neural network from learning the entire dynamical system to just learning a correction term. And this has been shown to allow for better training with fewer data. Today, the kind of gray boxing I'll show you is of a slightly different flavor. It's what I'm calling a more functional composition approach, where the idea is to approach a system with some domain knowledge, where you see which parts of the system you know a priori and which parts are maybe more difficult for you to know beforehand, and to focus the learning of the neural network on only the parts that may be difficult for you to know beforehand. And I'll explain that with an example. Going back to the URP-CSTR example, the black box learning is straightforward in that we just have the neural network learn the entire right-hand side function of the ODEs. When we stick to gray boxes, we can come in with some domain knowledge. From chemical engineering, from mass balances, we know that this is a flow system. So there will be some product or energy loss through flow, which comes from these two terms here, minus x1 and minus x2. Since we know that there is heat transfer to the surroundings, we can expect a heat transfer term of roughly this form. And we know that because there's reaction going on, that the product formation must have a generation term proportional to some sort of reaction term, and correspondingly there should be an energy generation term in the temperature that is also proportional to the same reaction term as in the concentration. So from this we can see which part of this do we want the neural network to learn. Here we felt that the hardest part for us to maybe know a priori would be what is the functional form of the reaction rate beforehand. For example, we may not know that the reaction rate is first order, second order, or some more complicated form. Here we now instead have the neural network learn just the reaction rate. So when the black box, the neural network had a two-dimensional output, in the gray box it just has a one-dimensional output, where it's now trying to learn this function phi, which is given by this form here. And given phi, we reconstruct back the white box, the ODEs in a white box manner as shown below here, with additional, and this in doing so also exposes some additional experimental parameters that the black box model wouldn't have known beforehand, such as B and beta. If we know the values of B and beta beforehand, for example, we have measured the heat transfer coefficient to know what the value of beta is, we can give it to the model as known parameters. Or if they're sufficiently identifiable, which in this case as they can be even given as additional training parameters to a neural network. So that the neural network, in addition to learning the reaction rate, can also fit these experimental parameters simultaneously. Again, demonstrating this on the pooled CSTM model, we can see that the GB2 model, which learns both the kinetic function and the experimental parameters, is able to learn the true phi or true reaction rate pretty well. Most of these points lie on the diagonal identity line. And when the white box, when the ODs are reconstructed in a white box manner, we also get really good prediction of the overall right-hand side for both variables, as shown from this diagram. And in long terms, the bifurcation diagram predictions are also very accurate. Furthermore, this model is also able to learn the right values of the experimental parameters B and beta, which are fit during training. So in this way, we have reintroduced physical intuition into our data-driven models, because now we can say that what the neural network is learning is a kinetic rate. And another benefit of this kind of gray boxing is in allowing us to extrapolate beyond the parameters space that we have trained the model on. And I'll demonstrate this with the GP1 model. Here we assume that the value of B and beta can be controlled and were known when training. So here, the neural network was only trained on one value of beta and one value of B, which are shown by these vertical dashed red lines on these diagrams here. And then we start to see, can we predict what the system behavior will be for values of beta and values of B that the system had not seen before? And so now we construct bifurcation diagrams, not with respect to the down color number, but now with respect to B and beta. And we can see that despite it have only learned on a single value of B and beta, we can actually reproduce these bifurcation diagrams to pretty good accuracy, even far away from the original training parameters. And in this way, we can see that if the gray boxing technique is done well, we can improve the generalizability of the final model. With that, I've demonstrated how this methodology can work on a simple toy example. Next, we want to show that this approach also extends to larger, more complex models. And so for that, we chose a biological example. This one is from Bolches and Fredrickson, and it is a model of microbial competition. It involves three microbial species, X, Y, and Z, and they interact with each other in a pseudo-predator-prey kind of interaction through the secretion and uptake of chemicals U, V, and G. So in this one, the important functions to care about are the microbial growth rate functions for each of these species, where mu1 corresponds to X, mu2 to Y, and mu3 to Z. Because of the predator-prey interactions, at steady state, the system stabilizes to a limit cycle. Here on the top right are the transient data with respect to time, where we can see that for the choice of parameters that we operated on, the microbe Y is selected against, so Y washes out the system, but X and Z oscillate out of phase in a predator-prey interaction, which also translates to oscillations in U, V, and G. Returning the same data instead in a limit cycle form, we get the bottom right diagram that the black curve here is the steady state limit cycle, and each of these are the same transients as here, but just now depicted on the limit cycle. So when training a black box model on the system, the black box model is straightforward again in the sense that the neural network just learns the entire right-hand side function of the system of ODEs. And the results of the black box model show that the black box model is able to learn right-hand side of each of the 6 ODs very effectively. All these points lie primarily on the identity diagonal. And in regards to the long-term limit cycle prediction, we also get very good prediction for what the limit cycle look like at steady state and good prediction of the limit cycle period as well. Next, we look at how can we also look to gray box this same model. Here again, we come in with domain knowledge and see what parts of this we may know a priori. For example, all of these terms ahead here with alpha, they are all full-related terms that can be derived from mass balances. Some parameters such as mu sub c can be obtained from simple experiments with just growing each of the strain in a single culture, because these are just single parameters, not functions. And the difficult part that we may not know beforehand is what exactly is the functional form of each of these growth rates. So here again, the neural network, rather than have 6-dimensional output in predicting the entire right-hand side, all 6 variables, now it has a 3-dimensional output, predicting just the functional form of mu1, mu2, and mu3. Again, we may have some additional coupling constants that we may not know beforehand, such as omega, rho, sigma, and eta. And so here we can also have these parameters be additional trainable parameters to the neural network if they're sufficiently identifiable. So the result of this model also show that the gray box model is able to learn the microbial growth predictions very well, shown by this figure on the bottom left. And when the ODEs are regenerated in a white box manner, we get good predictions of the RHS as shown on the top left. And a steady state limit cycle predictions actually even better than that of the black box model. When it comes to experimental predictions, this model is able to learn the right experimental parameters to a pretty good degree of accuracy. Some are learned better than others just because of the nature of the data, but they are very near the same magnitude and the same value. Next, I'll talk about some more interesting aspects that we saw. Hold on, there's something to chat. All right, so someone was asking about comparison of training times and resource requirements of black box and gray box model. So I find that the way I do the black box and gray box model, that I don't actually find much differences computing in computing power. The gray box model do train slightly slower, but it's not a significant amount. One thing I've definitely found is that the sometimes it can be harder to train the gray box models. Like I feel the main benefit of the neural networks, especially with activation functions such as ReLU, is that the loss landscape is such that gradient descent allows for very good convergence to the right minima. However, in gray box methods, when you introduce additional functions and limit it, I feel the loss landscape is affected. So sometimes the gray box models, I have to be a lot more careful as to how I normalize some of my inputs and outputs when calculating loss. I have to be a bit more careful as to how some of them are initialized than I may have been for the black box model. I hope that answered your question, but feel free to ask a follow-up. Next, I want to talk about some more of the interesting aspects that I found that I didn't expect. So, yeah, some interesting things that I saw that I would want to share with you because I didn't expect to see this kind of behavior. So one thing I saw is that sometimes if I found that my model for the Boltzmann and Fredrickson model, microbial model, converged to a very bad local minima. And the data pathology that this was trained on was that of full observations where at each time point, all 6 variables are measured, and data was sampled at a regular delta t of 8.33. This delta t was too large for the RK4 integrator, so I split it up into two iterations for each prediction into steps of 5 and 3.33. These are what I would have normally considered to be the ideal scenario where the data is very well structured and I've got full observation, so it should be easy to train. But I found that in some cases, I get this kind of behavior where if I were to recurse through the trained neural network at the same time steps, that I found that for the first time step of 5, the neural network would predict something that's magnitudes or a significant bit higher. And for next time point, it will jump back down and it'll keep doing this resonance style jumping back and forth. So what we can see from this is that this neural network is no longer learning the right-hand side of the underlying system of ODEs, but instead it's learning more of a time one map from one time point to the next by hard coding in the Runge-Kutta integrator into its forward prediction. And this can also be seen from this graph where I gave it the trained neural network back into SciPy as an ODE function, and I tried to use normal adaptive time step solvers to give a solution. And as you can see, it's not giving the right solution at all when it is treated as if it was the right-hand side function. So here we were looking at what different ways do we have to mitigate this kind of bad convergence. We'll talk about 3 strategies that worked for us. One thing that we saw first from looking at this top left figure here is that we saw that the output of neural networks were way higher than they should be. Like it was predicting a way bigger gradient than it should be, which can be seen from those very large magnitude jumps. So we propose that this could be an issue with a bad initialization of the neural network. And so what we did for the case of BFBBB is that it has the same training data as the A model, but now when I initialize the neural network, I also scaled down the weights of the output layer by a factor of 100. So I made it much, much smaller, hoping that it would bring it more in line to what the true ODE magnitude should be. And true enough, if when I trained it with this, just matching the output layer weights, now the network was converging to the right global minima. Another strategy I tried was I still kept the bad initialization of the A model, but now rather than always splitting up the delta t of 8.33 into 2 steps of 5, 2.33, I now randomized what time steps the solver takes. So it may take sometimes 4 and 4.33 or some arbitrary number. And by doing so, I want to break the hard coding of the RK4 iteration at every single point, and in doing so, completely remove this local minima. And this also was shown to work, that now the model was converging to the right kind of behavior. Oh, once again, I should mention that these bottom graphs, they were all in all the bottom graphs, the trained model was given as an input to a SciPy integrator, which uses adaptive time stepping to treat it as an RHS of an ODE. And finally, in the DA model, rather than chaining the solver time steps randomly, I try to see like if I were to resample data at random delta t's now, which would very naturally also randomize the solver time steps, because the solver has to step at the same time point as the data. That also very naturally dealt with or allowed the model to converge. So this was interesting because this was one example where actually having so-called messy data or randomly sampled data actually allowed the model to converge better than so-called well-organized data, even though this is admittedly a very niche example. Another interesting thing was that, as I mentioned before, when the initial condition is partially observed, I introduce extra tunable parameters to learn the right initial condition. So you may be wondering, am I actually able to learn the correct initial condition? And the answer is not exactly. So what I'm showing on this screen here, in the dashed lines here, I have in black, I have the true ODE that is integrated from the true initial condition that's given in black here. In dashed blue, it's the trained model starting from the true initial condition. And finally, in solid blue, I have the trained model starting from the learned initial condition. And from the difference between the two black and blue axes, you can see in some cases, the network does not learn the right initial condition, it learns something off. But we also see that even that the same model, the same trained model, when integrated from the true or the learned initial condition, the learned initial condition very quickly converges to the other trajectory. And to explain this, we explained this by talking about the separation of time scales that are in the system, which is similar to what we observe in singularly perturbed systems, where there's a fast manifold and a slow manifold. If you start the integration from off of the slow manifold, you would observe a very quick convergence down to a slow manifold, and then the system would evolve slowly on the slow manifold. So if you have a data point that is on or very near the slow manifold, you may find that you may have multiple initial conditions where, at least practically to numerical error, may be consistent with this condition because it would very quickly converge down and meet the exact same point. And that is similar to what we are seeing here, where this convergence happens at the time scale of the data samplings. Data samplings about every 8.33, the same time scale is happening. And at longer times, we can see that if you were to zoom this out and look at it over long times, that the true trajectories are actually indistinguishable from each other. And it's only in the beginning that we see this kind of disparity. So in conclusion, neural networks that are templated on numerical integrators can learn to be differential predictors. And these very naturally take delta t as an input, so this makes it compatible for training on data that have variable time steps. Next, this differential predictors also allow this to be compatible with many physical models, which is very conducive for incorporating existing knowledge and for gray boxing. Our use of teacher forcing simplifies training on partial observations, and here we use trainable initial conditions for when the initial conditions are also partially observed. And finally, gray box models can be made such that they're more physically intuitive, and they can actually be capable of extrapolating where the black box models are not. And with that, I would like to thank our funding agencies, and I'm happy to take any questions.
Thank you very much. Any questions or comments? Yeah, maybe I may have. Yeah, okay. Yeah, do you have a question?
No, he was just saying something.
Yeah, okay. No, I just thought someone else was talking. But the case of the noise one, can you just come back to it a little bit?
Sorry, the case of the what?
The one with noise, the multi-scale case. Yeah.
Oh yeah, I mean there wasn't noise in any of them, but it's just a larger dimension. Are you talking about this one?
No, it's about the next one, I guess. Yeah. Is the multi-scale one? Multi-scale, multiple scale?
Oh, yeah. This one?
Yeah, this is like yeah, exactly, singularly perturbed. So I was wondering if you add like a little noise to the right hand side for the slow and the fast, would this be still working? Because I mean this kind of like slow fast with noise, I mean they can be viewed as like models for systems with critical transition. So I wonder, yes, I wonder what would happen if you add a little bit of noise out there.
Adding noise to see